Okay, we are recording now. The only thing that we've talked about so far is that in a series circuit, when you have resistors lined up one after another in series, the equivalent resistance is going to increase, which, if the resistance is larger, then the current has a harder time flowing. So the rate of charge in coulombs per second is going to be reduced. In a parallel circuit, it's actually going to be just the opposite. Okay? Resistance is kind of a measure of how hard it is for current to flow. So as current comes out of the positive side of the battery, in a parallel circuit, it has a choice, right? We come to this point B right here, which is called a junction, and the current can either go down through the 4 ohm resistor, or it can go through the 16 ohm resistor. It is going to do both, right? And it's going to be proportional to the size of the resistance. But overall, in terms of sheer volume of charges being able to pass from the positive side of the battery to the negative side of the battery, that current is going to increase. So I kind of like to think of this in terms of trying to get to school in the morning. So Liberty is in between Custer and Independence. And you can imagine, well, if there's like a wreck on Custer, then overall the number of people getting to school on time is going to be reduced, right? But if both streets are wide open, then more cars can get from 121 to Rollator, okay, in the same amount of time. So the more pathways you open, the easier it is for current to flow. How can a battery release more current juice? A good question. So most batteries can release up to 2 amps of current, which is quite a bit. It really just depends on the amount of resistance that it encounters. So a battery has an internal resistor. I had several questions like on the Ohms Law lab about like what that internal resistor does. The internal resistor caps the amount of current at 2 amps. And it can always release less current than that, but generally it's going to cap at 2 amps. Great question. In a happy physics world, if you have, I have a 9-volt battery, is that a lie? I'm not sure what the maximum current for a 9 volt is. I'm kind of like scared to test it. I stole a bunch of stuff from school. I don't feel bad at all. No. I also don't know if this battery is alive or not, because I probably pulled this one out of my smoke alarm because I got tired of the beeping. What the maximum current is here. If I catch myself on fire, don't tell anyone how I died. All right, so that's pretty big. So the current here went up to, it was like 7 amps, which was a lot. So yes, the current in a 9-volt battery can be much higher. Very good. Excellent questions. So we have this 4 ohm resistor and the 16 ohm resistor in parallel. Okay. We have this idea of equivalent resistance where if we wanted to, be cheap, we only wanted to buy 1 resistor instead of 2, we could replace them with this equivalent resistor, which, well, if we're trying to keep this current flowing out of the battery as the same, then the resistor that we replace it with, this equivalent resistance, has to be smaller. Okay? In parallel, that equivalent resistance formula, it's 1 over R1 plus 1 over R2, and so on and so forth. So going back to this circuit, at this moment, I can't do anything with this series circuit because I don't know what R2 is, right? If I wanted to add it together, I know it's going to be 5 plus this question mark plus 8 would be my equivalent resistance. Okay, but until I figure that out, Can't do anything on this side. On this side, since I know both the 4 ohm and the 16 ohm resistor, I can say, all right, so 1 over the equivalent resistance is equal to 1/4 plus 1/16. See, my common denominator is going to be 16. This is going to be 4/16. All right, so 4/16 plus 1/16 is 5/16. So 1 over REQ is equal to 5/16. So REQ is going to be equal to 16 over 5 ohms, like so. We good so far? All right. When y'all went through the current notes, we talked about Kirchhoff's junction rule, and I clearly did not know how to spell Kirchhoff. It's fine. So Kirchhoff's junction rule says that what goes in must come out. I'll write that over here on the side. So in the context of a series circuit, there are no junctions, right? So I've got some amount of current being provided by the battery. That current is going to go into the 5 ohm resistor. It's not going to get trapped there. It's not going to like mysteriously vanish. It's not going to get used up. Okay, so the current that comes into the 5 ohm resistor is also going to come out of the 5 ohm resistor into this unknown resistor, out of this unknown resistor, into this 8 ohm resistor, and then out of the 8 ohm resistor, completing its path. Okay, so the application of Kirchhoff's junction rule in this circuit is that the current through all the resistors are the same. Since charge cannot be created or destroyed. That's what the junction rule says. In the parallel circuit, well, at junction B, we do have a choice. Okay, so we've got some amount of current I1 going into this crossroads, this corner. Okay, I know that, well, I have these 2 branches here. The current is going to divide amongst those 2 branches, not necessarily equally, but so that no charge is created or destroyed. I know that I1 must be equal to the sum of I2 plus I3. This charge can't be created or destroyed. Now, just speaking logically, if you were a charge and your dearest hopes and dreams were to get from the positive terminal of the battery to the negative terminal of the battery, which pathway would you rather take? The one with a smaller resistance or the one with a lot of resistance? Probably the one with the smaller resistance. So just by looking at the values that I have here, I know that I2 is going to be larger than I3, and if I were to really, really think hard, by what factor do we think I2 would be greater than I3? This is really hard to do if without an audience. I ask all these questions and it's just like silent. Because this resistor is 1/4 of the size of the other one, this branch is going to be able to support 4 times as much current. I'll just kind of make a note over here. Okay, so I2 is going to be 4 times as big as I3 because the 4 ohm is equal to 1/4 of the 16. Okay. So that's what's going on with junction rule. Can you explain the difference between current and voltage? Yes. So current is the number of charges that are passing by or passing through something. It's like the speed of the charge flow or the rate of the charge flow. Voltage is more like a pressure or like a push, right? It's how hard is this pushing? How much energy per unit charge is being converted into non-electrical energy types. So one of the examples that I gave to someone earlier is imagine that you have like a cup of water and then you have like a big gallon jug of water. Both of them are sitting on your kitchen counter. Okay, you dump out the cup of water and you dump out the gallon of water. Okay, both of those fell the same height. That's like voltage. And so both of those had the same voltage. But obviously the gallon of water had much more water in it. So there was more energy getting dissipated when you dumped out the gallon of water as opposed to the cup. Does that kind of make sense? So current has to do with like the sheer number of charges that are getting from point A to point B. Voltage has to do with the change in energy of each unit of charge as it passes through a resistor. Perfect. Okay. Actually, going back to this parallel circuit, I was given that I1 is equal to 12 amps. So I know that I2 plus I3 need to equal 12. And I also know that I2 is equal to 4 times I3. So I could do this. So I3 is going to be equal to 12 over 5 amps, which I have no idea what that is as a fraction. Anushka, I2 and I3 are not equal. I2 is going to be 4 times bigger than I3. You can kind of think of, if you want to go with the cars and traffic analogy, here's a street with 4 stop signs. Here is a street with 16 stop signs. All right, I set a timer for 5 minutes, right? There's going to be 4 times as many cars able to travel along this street as along this street. Does that make sense? Hello. Okay, so I2 and I3 aren't equal, but it is equal, like the sum of them is equal to the total amount of cars trying to get from the positive terminal to the negative. You can think of current one, it's like the total number of cars trying to get from, let's say, Liberty to 121. So that's just like the total amount that the battery is going to supply. Okay, so hold on, let me actually get a number for this. So 12 fifths is equal to, nope, not 2 fifths, 12 fifths is equal to 2.4 amps. Okay. So there are 12 cars total traveling from this side to that side. Okay, 2.4 of them are going to go, not through I2, but through over here, which means that 12 minus that. Okay, oops. 9.6 cars are going to travel through this 4 ohm resistor. Does that make sense? Did I answer your question? Good. So we've got essentially, maybe not cars, since hopefully you're not dividing cars in half, but you kind of get the idea, right? Got 12 cars going from this side to that side in some amount of time. 9.6 cars are going to be able to go through this path at the same time that 2.4 cars are going to be able to go through this path. Cool. Okay, and then the series one is really easy because the current is going to be the same all the way through. All right. So that's about current. Kirchhoff's loop rule talks about voltage, and I know voltage was the thing for today. So bear with me, ask for explanation if I go too fast here. Voltage is like the amount of energy per coulomb of charge that gets converted into something else. Okay, so if this were like a 12-volt battery or something right here, that means that a coulomb of charge at this point would have 12 joules of energy. In order to get around to the other side, at this point right here, a charge would have 0 joules of energy. This is kind of like a charge pump. Going with the water analogy, it's like a fountain, you know, it like sprays water upwards. It's kind of like that. Okay, so it takes still charges and it gives them a velocity. So Kirchhoff's loop rule essentially says what goes up must come down. So Kirchhoff's loop rule says that the potential difference going all the way around the circuit has got to be equal to 0. It's a conservation of energy implication, or it's a result of conservation of energy. So let's see, what does it tell us? It says that our voltage between C and D, so here our unknown resistor, has a voltage of 20. A lot of times when we are talking about voltage, we just keep it positive because it's implied that it's the magnitude of the energy change. Okay. Your batteries increase your electrical energy, your resistors decrease your electrical energy by converting it into something else. All right, so this is going to drop 20. The voltage between C and B, oh, it's going to be right here across this resistor, is going to be 80 volts. Okay. Y'all did that lab on Ohm's Law, right? V is equal to I times R. For this resistor, I can figure out the current going through it. I'm given the voltage across the specific resistor, and I'm given the resistance of this resistor. So the current traveling through the 5 ohm resistor is going to be equal to 80 volts divided by 5 ohms. 80 divided by 5, 16. And so this is kind of cool. We get to go back. We're like, oh, this is super boring. Kirchhoff's junction rule through a series circuit. That means the current through all the resistors is the same, which means we can now figure out what R2 is. Okay, so for R2, right, Ohm's law is still going to apply. R2 is going to be equal to 20 volts divided by 16 amps, because this current is the same throughout. Okay. Now, you know, going through our little scenario, 16 cars are traveling along. 16 cars make it through this intersection, this stoplight. All right. 16 cars are going to make it through this stoplight, this intersection. Well, it's not really an intersection. It's just like a stop. Right. And then 16 cars are going to make it through this intersection as well. No cars are getting abducted by aliens. No cars are going to like go off the road into a ditch. What goes in must come out. Okay, so 20 divided by 16 is 1.25. So resistor R2, 1.25. I could figure out what my total equivalent resistance is now, because I could just do 5 plus 1.25 plus 8. Let's go ahead and do that. Okay, okay. Then I can figure out what the voltage across this 8 ohm resistor is, because I know the resistance and I know the current. So let's see, do I have another color? I've been having a really good time with my fountain pens since I've been like all alone in isolation. A bunch of different ink colors going here. So for this one, it's going to be, we're trying to find the voltage. And so the current is 16. The resistance is 8. 16 times 8. Wow, it's a big resistance. So the voltage across that resistor that is between A and B is going to be 128 volts. So what goes up must come down. In this case, we figured out what has gone down. We've got 80 plus 20 plus 128, so 80 plus 20 is 100. We fell 228 meters or 228 volts. Okay, what does that mean about the voltage of the battery? Well, what goes up must come down. If I fell 228 volts, then the battery must have lifted us to 228 volts. Okay. So let's check this out. So we've been doing Ohm's law for these individual resistors. You can also do Ohm's law for your equivalent resistor circuit, all right, which would be like, okay, so we've got this battery, and then we've got this single equivalent resistor that is 14.25. Okay. And we figured out that the current through, or the current provided by the battery is 16 amps. So let's check and make sure that Ohm's law is actually working for this circuit. And so that's the kind of the difference there. You do Ohm's law for individual resistors. You can also do Ohm's law for your equivalent resistor circuit, and both of them should work out. Fingers crossed. 16 times 14.25 is in fact 228. So you can always check your work. It's kind of like doing Sudoku. You have like a lot of checks and balances, and if you screw one of these things up, you have to start over. So yeah, how does Kirchhoff's loop rule apply to the circuit? What goes up must come down. The battery voltage, the rise that you get from the battery must be equal to the total voltage drops of all your resistors. You would write a loop rule equation, something like this. So V battery minus the voltage across the 5 ohm resistor minus the voltage across resistor 2, which ended up being 1.25 ohms, minus the voltage across the 8 ohm resistor is equal to 0. Okay? So from this expression, practically speaking, if you're trying to solve a problem for this, you would replace each of these resistor voltages with I times R for the individual resistor. The next part, since we're still talking about Ohm's law, is the voltage across the resistor directly or inversely related to its resistance? Well, for the 5 one, we had 20. For the 1.251, oh, it's very small, we had 20. Did I say 20 twice? Sorry, whatever. And then for the 8 ohm one, we had a really big voltage, not of 80, but of 128. So that is a direct relationship there. All right, we'll finish this out. Power is the product of current and voltage. So you could go through and you can multiply current times voltage for each one. For a series circuit, it's frequently convenient. If you replace V with I times R, you end up with I squared R. In a series circuit, this is the same throughout. So we are just looking for the one with the biggest resistance. That's the one that's going to be the brightest. Right, so the physical feature that we're looking for with power is brightness there. So that's going to be the 8 ohm resistor. All right. So or any questions so far? Speak now for hold your peace. All right, we're going. For this parallel circuit, what goes up must come down. This is like, again, going back to the cup of water and the gallon of water. Both of them fall the same amount. So in a parallel circuit, the voltage across each parallel branch is going to be the same. The parallel branches are going to drop the same voltage, which we can confirm over here. We know the current I2, we know the current I3. We can find through Ohm's law for the individual resistors what the voltage is across each one. So we've got 9.6 times 4, which gives me 38.4. volts. We can confirm that we get the same thing on the other side. So the current there is 2.4 times 16. Hey, what do you know? All right, so both the voltage across the 4 ohm resistor and the voltage across the 16 ohm resistor and the voltage across the battery is equal to 38.4 volts. If we were to write a loop rule equation, well, since we have 2 branches, we actually have 2 possibilities, okay, for possible paths that we could travel. And I did this in the voltage notes, so take a look at those if you haven't already. Okay, so usually I start here, right, at the negative terminal of the battery. I climb up 38.4 volts. So right now I'm chilling. I got 38.4 volts for each coulomb of charge I have. Okay, when I get to this crossroads, a charge, have to make a choice. I choose to go through this one. Okay, as I pass through this 4 ohm resistor, I know that at this point right here, my voltage is supposed to be 0 again. So here I've got 38.4 volts. I'm going to drop all of my voltage through that resistor so that I end up with 0 there. So one of the equations would be voltage of the battery minus the voltage across the 4 ohm resistor must be equal to 0. For my second path, or my second option, all right, I'll start at the same place. I will be here. I will climb up 38.4 volts. I will not turn right immediately. I will keep on going straight. And I get to the 16 ohm resistor and I'm like, well, on the other side of the 16 ohm resistor, this is 0. So I must drop 38.4 volts to get back down to 0. There is something we can do with color coding to help us recognize how the voltage changes across resistors. A resistor is always going to decrease the amount of energy that is available. So here at the beginning, right? We have lots and lots of voltage, lots and lots, and that voltage, that energy isn't going to be dissipated until those charges are able to pass through a resistor. Okay. So if I were to grab my multimeter, have, one end over here, and then I touched anywhere along these lines, right, the voltage reading would be 38.4 volts. On the other side, this is, usually we say like this is like voltage equals 0 over here. And it's all based on the change in voltage. Just like how gravitational potential energy is always based on the change in height. Same sort of deal there. Okay? So no matter where you look, right, if you go one side of your voltmeter on blue, one side of your voltmeter on red, you should get 38.4 volts for each one. We can do the same sort of thing with this series circuit. Okay? So here, on the positive terminal of the battery, we are full up on voltage, like so. Right here on the negative side of the battery, we are coloring this blue to indicate our charges have no energy here. They're fixing to go through our charge pump, the battery. Okay, so the stuff that's happening in the middle, if I had more colors than just these, I would make a beautiful rainbow for y'all to see, but I don't. I'm limited. I'm sorry. So the color change, the voltage drop from here to here is 80. So I'm going to say that this is represented with orange. Okay. So the voltage drop associated with the color change between red and orange is 80. Okay. Going from that to blue, I don't know, we'll color this green. Not to scale. So going from orange to green along the rainbow, the voltage drop associated with this is going to be 20 volts. Okay, and then from green to blue is going to be 128 volts. Okay. So within the resistor itself, it's kind of like this gradient thing. The resistor dissipates that energy, like so. That's color coding. We'll do some more examples with that here as soon as we finish getting through this. So according to Ohm's law, is the current through a resistor in parallel directly or inversely related to its resistance? Well, over here, as more and more resistors are added, more and more pathways become available. Just thinking about Ohm's law, V is equal to I times R, right? V is going to be the same across each branch. So the smaller the resistor, the more current that's going to be able to flow. Okay, and that is an inverse relationship. Going to power, so power is defined as the current times the voltage. If I wanted to be cute, V is equal to I times R, I is equal to V over R. So if I were to plug this relationship into my power formula, I would get V over R times V. So power is equal to V squared over R. So we kind of have, we have 3 power equations total. This one is really convenient to use in your series circuit since the current is the same everywhere. In your parallel branches, the voltages are what's the same from branch to branch. So same voltage is applied both the 4 ohm and the 16 ohm resistors. If you have a small number in the denominator, it makes this number bigger. So in this case, the 4 ohm resistor is the one that's using the most power. Okay, it's going to be, again, going back to the water cup versus the gallon full of water analogy. This one is like the gallon full of water. And this one is like just the cup full of water. And we've got a very narrow stream kind of going on here, as opposed to the gallon. Whew. All right. Any questions on that? I will post this video on Canvas. I will post this paper on Canvas as well. I have some samples. Yes, there is a complex one. How exciting. I would like to analyze this one real quick. So this one is fun. It's complicated. Do I know what that resistor is? My goodness, my goodness. I do not. Oh, so exciting. So I can color code this though, right? Let's start with that. So the positive side of my battery has the most energy. All right, so any plain wire that is before a resistor is going to have this maximum energy. Those electrons, well, the conventional current is buzzing. It is full of energy, just waiting to be spent. Okay. This side of the battery, the negative side, these charges are still moving, right? But they are very lethargic. They don't really have the ability to do any more energy conversions. They're just kind of scooting along their way. Okay. So something like that. Okay. Getting from red to blue, well, there's a number of colors in between red and blue. Let's pick green, right, to indicate that, right, this voltage, so red to green to blue, is essentially going to be the same total as going from red to blue. It's just we're kind of taking a step in the middle. Okay. Let's see what numbers they gave us. Let's see. They said that the voltage across A and B is 24. Which means that the voltage across this resistor, if we were to put a voltmeter in here, like so, it would also be reading 24 volts. If I were to take my voltmeter and straddle both of these resistors, it would be 24, but I don't know individually what this one is and what that one is, okay, not yet. It tells us that the total current is equal to 6. So this current right here coming around is equal to 6 amps. All right, so I know my total voltage and I know my total current. So with this, I can do Ohm's law with Req. All right, so V battery is equal to I total times Req. Solving this for Req, it's going to be VV over I total, which is going to be, oh, that's so nice. Look at that. My equivalent resistance is 4 ohms. I was using RT here for R total. It's better to call it Req. All right, so my equivalent resistance is equal to 4 ohms. And now I get to kind of work backwards, right? I have essentially 2 branches that are in parallel, right? I don't know what this resistor is, but I know that 1 over 4 needs to be equal to 1 over 8 plus 1 over something. where this something is going to be the sum of these two resistors. So this is going to be 1/8 as well, right? 1/8 plus 1/8 is 2/8, which is 1/4. So that means our DC plus 6 is equal to 8. I did that a little fast. Did y'all follow? This 1/8? Yeah, so essentially 1/4 is equal to 2/8. So 1/8 plus something needs to equal 2/8. So this is for the parallel branches. So this equivalent resistance and this sum equivalent resistance. Does that make sense? It's very much like a puzzle. So that means that now, if this whole branch is supposed to have an equivalent resistance of 8, and I've got two resistors in series, well, one of them is 6, the other one's got to be 2 in order to get us to 8. Let's see. What are we looking for now? Oh, well, I2 and I3 are going to be equal. That's nice. Because this branch has 8 ohms of equivalent resistance. This branch also has 8 ohms of equivalent resistance. So 3 amps, 3 amps. We could also figure out the voltage across each of these resistors as well, now that we know what the current is flowing through both of these. So 3 times 2 is 6 volts. 3 times 6 is 18 volts. Let's double check and make sure that what is going up is in fact coming down. If I do loop rule for this outer branch, I have plus 24, minus 2, oh wait, no, sorry, minus 6, got scared. 24 minus 6 is 18, and then 18 minus 18 is 0. So loop rule confirmed. Okay. And thinking about Ohm's law for your individual circuits, right? It makes sense that the voltage across this small resistor is smaller than the voltage across this big resistor. If you notice, the ratio is even the same, right? Compare 2 to 6. 6 is 3 times bigger than 2. Right? The voltage across that 6 ohm resistor is 3 times bigger than the voltage across the 2 ohm resistor. All right. What questions do you have? Cool. Well, I will post this on Canvas. Let me go ahead and stop recording.